Hello all and welcome back to this course on computer organization. So having familiarized ourselves with many different assembly instructions, we can now move to the next level where we are going to try and use assembly language and C programming together. Okay, and the idea of that is what we call inline assembly. Okay, so in the last week you would have noticed that when we discussed simple assembly programs like multiplying two numbers, and adding, subtracting, we just I glossed over a certain notation. Okay, I said int x equal to 4, y equal to 6, and then I did something, underscore ASM bracket. I didn't talk about all of that. I simply went ahead and wrote out this assembly program for you, right? Just explained how to move data into a register, perform multiplication, subtraction, addition, whatever it is, right? It doesn't matter. But the real point is that all those other details have been glossed over last week, and this week I wish to put all of that in right perspective. Okay, so the base for us is always a C program. Okay, and the idea is very simple. You start with a C program like this, and let's say int x equal to 40, y equal to some 30, a equal to 45, b equal to 55, and then I'm going to go ahead and implement that particular function, which is basically x into y plus a minus b, and store it in, let's say, another variable z or u. Okay, I have u comma v, where I intend to store u equal to x into y plus a minus b. Okay, so this is going to be 40 into 30 plus 45 minus 55. So 40 into 30 is 1200 minus 10, you should get 1190 as the answer, right? So this is the idea. So of course, if I were to do this in a C program, it would be as simple as just doing this: x into y plus a minus b. Okay, and then I can do printf z equals %d. Okay, maybe I'll write this in the next line because printf z equals %d slash n comma or u, right? So the expected output of this program should be u equal to 1190, right? This is what we expect, and this is how we would code a typical C program, right? Of course, remember, you have to do the necessary hash include stdio.h. Okay, now the idea of inline assembly is certain parts of a C program we can technically move to assembly language programming because we might want to speed it up, we might want to exploit certain assembly instructions, right? So later in this course we will look at how this C program is actually taken to assembly, right? Every single instruction that the compiler generates, we will be able to explain, we will be able to generate ourselves. But suppose the compiler does not exploit a certain instruction very well, right? For example, we looked at the string operations of the x86 architecture, which does hardware loops and all that stuff, and they can be used very efficiently to do some very complex functionality. But maybe the compiler does not know how to use this, the compiler is outdated and is not able to use these instructions, and maybe as a designer or as a programmer you want to use these instructions effectively. So what you will do is, you will basically take the same as a C program. Okay, I will not rewrite the whole thing, I'll just copy this, right? I'll just copy this to the next page, right? And then right, I'll just do this and I'll move this down, right? The aim is ultimately the output of this program should still be this only. Okay, we don't want anything else. So instead of doing this operation, which I will comment out now like this, I am going to switch to assembly language programming. __ASM is how I start, and I'll put this in a closing bracket here, flower bracket. So whatever I write inside this __ASM will get interpreted as assembly instructions. So inside this __ASM, if you go and write C statements, it will give you a compiler error, right? You go and write a printf or a scanf or something, it will give you compiler error. That's not going to work. So don't do that. What you're going to do here is you are now going to try and write the equivalent of this statement in assembly language. So now that is exactly what you saw last week when I started this thing. You know, you went from int x equal to 4 something __ASM and then started writing out some assembly code. This is exactly what we are going to do now. So in order to do x into y, I told you that the EAX register has to be used as one of the implicit operands. So I typically will move EAX comma x. Now what is x is a very good question, because x, as far as the microprocessor is concerned, should mean something. It should either be a register value or it should be a memory location, but for now we are going to ignore that completely. We are going to treat this as an abstraction. We are going to, let's say this x, y, z is either memory or register, we don't care, right? But it is a valid assembly instruction, right? So I am going to move x into EAX, right? And then I will do mul of what? Y. Okay, so what does this instruction do? EAX is equal to x. After executing this instruction, EAX will get x into y, right? Then I do add EAX comma A. So here EAX will be x into y plus A, and finally you subtract EAX comma B. So you are saying EAX equals x into y plus A minus B. Okay, now of course the answer that we have generated or that we have calculated is still in EAX, okay, but I want that answer to go into the variable u, and for that reason I need to add one more instruction, which is move u comma EAX, okay, and then I will close the bracket here. Okay, please note I will put this in red so that it is evident that I am switching to assembly. ASM. I will close this bracket here. Okay, so the final statement here is what is going to set u to EAX, that is x into y. Now if I go ahead and do the same printf u equal to %d comma whatever value, I should get exactly the same value, right? So this is, of course, you know, again the syntax of __ASM, flower bracket open and all that stuff is very specific to the compiler, and that's why it is important. And I told you that we are going to tie ourselves to MSVC compiler. Okay, this is the compiler, Microsoft Visual C compiler, and we are talking of x86. The move EAX comma x and all is x86 instruction set, right, instruction set, and so on. Okay, so now where do we go ahead and code all these things, right, so that we can check our answers, and where do we practice and how do we practice? Okay, so the idea is to basically we are going to go to this website, okay, called godbolt.org. Okay, so if you go here and you click on this, you will get the whole thing. It's basically godbolt.org. Okay, and so what you must do first of all is to set the language here to C. Okay, and also please set this option, the compiler, because it's going to ask you to select a compiler. Okay, you set this to x86 MSVC v19.latest. This exact thing does not matter whether you use v19 latest or s17.10, whatever. I don't think that really matters, but make sure you choose MSVC v19.latest to be safe. Okay, now what you go ahead and do is to sort of set this compiler, and on the left pane here you just go ahead and write your C program. Okay, C program as it is. So as you can see here, what I have done is I have written out exactly the same program where I have said x equal to 20, y equal to 30, a equal to 44, b equal to 55. Arbitrarily I have initialized it, and I have said, okay, instead of u I have said z. Okay, so actually if you want to keep it consistent, then I must call this u. Okay, u equals, of course now you will get a compiler error because z is undefined, so I have to do this. Okay, so as soon as you write your code, the code gets compiled. Okay, and what you see on this right hand pane, the second pane here, is basically the so let me just come here. Yeah. Okay, so I'll close this third window for now. The second window that you see, clearly you can see assembly instructions that you recognize. Okay, push, pop, move, sub, add, mul, imul, it doesn't matter, right? It's basically a whole bunch of assembly instructions that we are dealing with. Okay, so now what we are going to do is we basically have the x into y plus a minus b, right? And we are doing a printf. Okay, so now what I want to do, I'm going to go ahead and do exactly the same thing that I did. I'll comment this out, which means that I am not doing x into y plus a minus b in the C code. I'm going to go to switch to assembly language here. Okay, I'm going to write underscore ASM, and then I'll do move EAX comma X. Okay, I'm going to use lowercase because I don't remember if this is case sensitive or not, but it doesn't matter in the course. When we write instructions, I write it in uppercase, but here you might have to do lowercase. So let's try that. What happens if I do comma X, right? I don't know if this is case sensitive. So yeah, so this also works, so no problem. So maybe I'll just do this in uppercase for now, and then I'll do mul, okay, of y. That's the next instruction. Okay, so at this point you should have x into y being stored in EAX. Okay, and then I'll do add EAX comma A, and then I'll do sub EAX comma B. Right, of course this is going to take a little bit of time to compile, and of course the answer, now if I just go ahead and look at the execution of this code, it's not going to give me the right answer because u has not been initialized with the answer that is in EAX. So I do move u comma EAX. Okay. So this portion of assembly code now is equivalent to that arithmetic operations, sequence of arithmetic operations that we had in C code earlier. Okay. Now, what is the answer, by the way, right? What is the answer for this thing, before we go ahead and check whether this assembly code is correct? So let me just keep this. I'll go back to my C code itself, right? And after that, I'm doing a printf u equal to %d comma small u, right? So on the right hand side, like I told you, this gives you the assembly code for the x86 architecture that we have chosen here, x86 and the MSVC compiler. Okay, both the combination of these two is important to get this compiled correctly. If you choose another compiler, you will not even get that output correctly. Okay, it will give all sorts of errors. It will give compiler errors. Now, how do I execute my code and check? For that, you go and click on this output window that I showed you here, right? So if you don't have the window, you come to the bottom, click on output, right? It's going to tell you, of course, if there is a compiler error, for example, if I miss this semicolon, right, then what is going to happen? It is going to tell you that the compilation failed in the second window, but you have no idea what the error is or where the error is. So you click on that output again, you will see on the third window here, syntax error missing semicolon. So you go ahead and put the semicolon, everything will be all right, and it will execute the code. Now, when you try to execute initially, unless this option is checked, execute the code, it will not explicitly execute the code and give you the output, right? If you just say if you just say compile, then it will just dump out the compiled assembly code for you. Okay, in order to make it execute the code, you have to go and click on this thing saying explicitly, asking it to execute that code as well. So execution means compilation, it will do something, it will generate an executable, and the executable then will be run, okay, on this is being run in the background in some server. So you get the answer u equal to 589. This is what the C code gave us. And is that correct? Yeah, 20 into 30 is 600, plus 44 minus 55 is minus 11. So answer is 589, which makes a whole lot of sense. Now what I'll do, I will come here, comment this part out, right, and I am going to now put this assembly code in there, okay. So you see that effectively it has performed this thing very correctly. Now let's say I leave out this sub EAX comma B, right. Of course it will compile, it will give you the answer, but the answer will be 644. Why? Because it is doing 20 into 30 plus 44. So you will get 644 as the answer. So you see that whatever assembly code we wrote now indeed does give exactly the same answer for the inputs that we have given, and therefore we know that this is a correct assembly code. So this is a wonderful place for you to come and practice your assembly instructions and assembly language programs as well. Okay, so let's come back here. Let's say now I'm going to modify this program to do X, XOR Y or A and B. Okay, this is something that we are going to do now. So earlier I wanted U equal to X into Y plus A minus B. Now I want to do additionally X XOR Y, right, or A and B. I hope this is correct, right? Yeah, very good. So now remember that earlier also I told you that we have added brackets, and therefore the order in which you do this is very, very important. Okay, so if I want to now do this, what should I do? I'll just go back and let me copy this program again, right? I have basically made a copy of this program, and I'm going to move this sufficiently below now, right? And then I'm going to add more assembly code so that I can implement the other part as well. So this is the close bracket. So now what do I do? So note that in this section of assembly code, I have used registers EAX and all that stuff to do some operations, and then I put the answer back into U, okay, into the variable U. Therefore, I can reuse the same EAX, EBX, CCX registers for any other operation. So the idea is very simple. These general purpose registers should be used for an operation and then freed up so that it can be used for other operations. If you try to store a state in that, you must be very careful, because if you use it for something, the state may get overwritten. Okay, so in this case, it's very evident that I have already stored the answer back into U, and therefore EAX is now available again for my operation. So I will again start by saying move EAX comma X, okay, and then I will do XOR EAX comma Y. Okay, this is saying EAX equals X. This is EAX now is X XOR Y. Okay, then I am going to do, remember, move EBX comma A. Okay, equal to A, and then I am going to do AND EBX comma B. Okay, EBX comma B. So now EBX will be A and B, right? And what do I do finally? I have to now OR what is in EAX and EBX. So I will do OR EAX comma EBX. So EAX will be the OR of EBX. Okay. Now of course I have not put this answer back into U, for which I am going to just maybe I have to move this code a little up. Move this code a little up here. Right, so I'll move this a little bit down, and then I am going to say move the answer which is in EAX into the variable V, right, and then I will close my underscore ASM operation. So this is going to say V equals EAX, or the ultimate operation, which is X XOR Y or A and B. Okay, so now what I'll do is I'll go and modify this program. Okay, I'm going to introduce the second variable. Okay, and so V I am going to now evaluate in C itself, X XOR Y, right, or A ampersand B, right. So good, so that is correct, it has been able to do it, and I will then change my printf to display V as well, comma V. Okay, so this is the C code that is supposed to now give me. So what does it do? It gives me V equal to this %D, yeah, absolutely. So it has given me V equal to 46 as the answer. Okay, Now, what does this XOR and all that stuff do? It basically does bitwise operations. Okay, so whatever the hexadecimal value of 20 is, it is doing a bitwise XOR with what the hexadecimal value of 30 is. Then it's doing 44 ampersand and 55 in hexadecimal bitwise, and then doing an OR. Okay, effectively it's now eventually giving you an answer 46. So I am going to now code this in assembly again and see if this thing is correct. Okay, XOR EAX comma Y, then move EBX comma A and EBX comma B. This is a compiler error, should be comma, right? And eventually I do or EAX comma EBX. Okay, and of course the answer is now in EAX, and therefore I move into V, my answer EAX. Okay, so important to note that I have to comment this line out so that the V gets evaluated in the assembly code and not in this. So now you see that the answer is still V equal to 46, which is exactly what we had obtained even from the C code, right? So with this technique, what you can do is move certain sections of your C program into assembly like this, but when you want to come back to more complicated functions, for example printf, right? Printf is a function that is used to display something on the screen. Internally it is coded in a very complicated manner. It takes care of so many things and then displays characters on the screen for you, right? Now imagine having to code that in assembly language, right? Somebody did, but for us to do it from scratch is a big pain, right? And that's why in order to learn assembly language, this is a very useful tool where you are focusing only on your sub operation to do some assembly coding, and then you switch back to C where it is convenient and do more complex things out there and verify if your answers are all correct, right? So this Godbolt Compiler Explorer with this setting is something we will continue to use at least till about half the course, right? It's a very powerful tool, so please do get used to it. Start practicing your assembly programs on this, and going forward I will explain to you exactly how all these lines of code were generated, right? And what it actually means to do all of this in assembly language.